Okay, we're going to pick up with where we left off in class. Uh, this is going to just continue with handout number 6 that we started here today. So let's go ahead and get started then. So as I said, this is for Stat 210, handout 6, pages 10 through 13, and this is for my absence on Friday, March 1st. So let's go ahead and continue with where we left off in class. In class, we were talking about measuring the distance between the observed and the expected outcomes. Okay, so we had, in this particular problem, the expected was all the same, and they were set at a quantity of 25.75, and I was just measuring the distance between my observed data and those expected values. So when we were doing that, we're just going to take the observed value for fall, here on the screen, 32 minus the 25.75, I get 6.25. 17 minus the 25.75, and I end up with negative 8.75. On these others, I'm going to take 30 minus 25.75. I think when I do that math, I get 4.25. And then finally, 24 minus 25.75. And when I do that math, I think I end up with negative 1.75. Now, when we add all of these up across all four of those categories, we're going to end up with 0. Okay, so that's a problem. So let's go ahead. We're going to get 0 when we do that. And why that's happening is because all of these positive distances are actually canceling out the negative distances here. So you can kind of see that that average there of 25.75 is just splitting all of those observed values, excuse me. So we end up getting a canceling out effect between the positive and the negative values. There's two different ways that we can get rid of this or deal with this. We can either take the absolute values of these quantities, so that certainly will get rid of the negatives. And the other is we could actually square these quantities. So we have options here between taking the absolute value or squaring. Now what we actually do is use the squaring. And the reason we do that is just because of the theory that is involved with this test. It's going to be a little bit more convenient to use squared distances than the absolute value distances. Again, I mentioned in class that a squared or a squaring function that has squares in it is a little more well behaved than absolute values when you think of derivatives and such. So what we actually end up doing here is taking those distances, so the 32 minus the 25.75, so that difference is 6.25, but I'm going to square that thing. So how we're getting this 39.06 is by taking that 6.25 and squaring it. That's where that number is coming from. Now here for the winter season, I'm going to take that negative 8.75 and I'm going to square that as well. So that's where that 56.56 is coming from. And then obviously when I do that squaring, I get rid of the negative here. So this is, where did this one come from? The 4.25 squared. The 4.25 squared is where we're getting 18.06. And then finally, the negative 1.75 squared is where we're getting the 3.06 value from. And now I'm going to just sum all of those up across all of those groups, and I get a value of 137. So this is what I'm going to call now our data value. Okay, so if you'd let me just call that data value. It's not really the data value because my data values are 32, 17, 30, and 24. However, I had to go through this process of condensing all of my data down to a particular number. Again, I'm doing that so that I can create a single pyramid. And in this case, that single number is 137. The goal now is to figure out whether or not the 137 is an outlier. So from my data, I condensed my information down. I did some squaring here. I did some differencing and then squaring. I condensed that down to a value of 137. But now I need to figure out whether or not 137 is an outlier. Okay, So I don't really know what my pyramid looks like yet, right? So my pyramid, if my pyramid has this type of pattern here, then 137 is not going to be an outlier. Or if my pyramid is down here, then 137 is going to be an outlier. I need to figure out where this reference distribution sits in order to figure out whether or not 137 is indeed an outlier. So that's what we're going to do next here, is figure out how to get that reference distribution. Now, in order to get the reference distribution, what I'm going to do is go back to something that we did earlier today in class. And that is, so let me go back to where I had Jump create the samples for me, where I was pulling them out of the hat. So I'm going to go way back to page 4 here a minute. Again, StatKey doesn't have this easily set up for us to do these simulations for a situation where I have several parameters. So page 4 here shows you just how to set that up in Jump. And then I can go ahead and get those repeated samples. So for this first example here, or this first repeated sample, I got the values 14, 29, 24, and 36. For the second one, I got 24, 20, 27, 32, you can see here, and so on. And I know that these values here were generated under a situation in which the crimes were occurring equally. So I got those parameter values being set here at 25%, 25%, 25%, 25%. So I'm going to take that differencing, do the squaring, and do the summing with these values now. So I'm going to take 14 minus the 25.75, square that. Take 29 minus the 25.75, square that. I just want to do the same exact process that I did to my data with these values in order to build the reference distribution. So now let's go back down where we were building those reference distributions. Let me see what page that was on. Page 12 it looks like. So that's what I'm doing on page 12 here. I'm taking those values as I just said, 14 minus the 25.75, square that, I get 138. I take the spring value, which is 29.29 minus the 25.75. I do that for all 4 seasons, and then I add those up. I do exactly the same analysis or calculations, I guess, maybe is a better word, that I did for the original data. So the original data, again, I got, what, a value of 137, was it up here? Okay, I think it was 137 here. I need to do this same exact process, okay, with the data from my simulation. So that first simulation resulted in a value of 257. So I can go ahead and put a X there at 257. Let me go ahead and do that. That's going to be, let's see here, that's 137. 257 is going to be probably somewhere like that. Maybe a little bit further out. The second iteration, so let's go up and look at what I did with the second iteration. Here I'm going to, again, we do the math here, I'm going to take 24 minus 25.75. I square that. Okay, whatever that quantity is there. Let's go ahead and do a couple of these, I guess. 24 minus 25.75, and then I need to square that. I get 3.0625 here. And then I'm going to keep doing that for each of those other seasons as well. Okay, so here I'm going to take 20 minus the 25.75, square that all the way down. So I'm going to get another value. It looks like on the second iteration, looks like I already added that up for you, was a value of 77. So that's going to be back here. And then I just keep doing this for several, and we could do hundreds or we could do thousands of different dots. So I could just repeat doing that. Now what's going to happen is we're going to end up with a bunch of dots kind of down here around 0. Okay? And the reason we're going to end up with a bunch of dots down around 0 is because we were generating these under a situation of being where the crimes were occurring equally, 25% in each of the seasons. So kind of over the many iterations, these are going to stay pretty close to 25.75. So that means when I go to difference them and square them, I should end up with quite a few small values here. All right, so on these reference distributions, we tend to have values that are close to 0 here. Now the upper end this is kind of what we call skewed to the right, because the upper end we could just get some kind of unusual outcomes from our simulation, like this one here, a 14, a differencing and then squaring. That's going to contribute that's going to add a lot to this 257 here. And here's a 36. Okay, so it is possible that I get some larger values here. But again, the goal is just to figure out to what degree 137 is an outlier. So our reference distributions are going to have kind of a pattern. Here's one here where I calculated that for 100 different repeated outcomes. Now, if I'm down close to 0 on this reference distribution, okay, that's the the equal, that would be crimes equal here. If I'm really big on this reference distribution, then that's going to be crimes unequal. Crimes occurring unequally across the seasons. Okay, so when I'm doing my p-value here, I want, again, the p-value are values that are as extreme or more extreme that are going to support my research question. Well, values to the right here support my research question. I said today in class that the test that we're learning about here in handout number 6 is a two-sided test. And in fact, it is a two-sided test. If we go back up here and think about what we're trying to do, we're trying to figure out whether or not they are far enough away from their expected. So if we go back to our pyramids, this is indeed a two-sided test, because if it was way lower, if some of these were way lower than they expected, that would suggest that the crimes are occurring unequally. Or if we're really high, it would suggest that the crimes are occurring unequally. So this is indeed a two-sided test. However, when I go to count the p-value, or when I go to count which observations support the research question, I'm going to be counting values only to the right. And the reason I'm doing that is because this negative 8.75, this distance here for winter, when I square that, that becomes a positive value. Becomes quite a large positive value. So all of my negative distances become positive values when I go through the squaring. So what that means in terms of my p-value is I only want to be counting dots to the right here, because these up here, again, say that I'm far away from what I expect. The squaring ensures that it's these values way up here, the high values here. I don't have to worry about being very low because of the squaring that's done. So anything that's far away from what I expect are going to be positive values here. And for that reason, I'm counting only values to the right. But again, I'll say this one more time. This test is a two-sided test. It's just that I'm counting p-values on only one side. In this particular case, there were 16 dots that were at 137 or higher. So the p-value here would be 0.16. So collectively overall, I guess as we talked in class, we do not have enough evidence to say that I have differences across the seasons. This one p-value here is not less than 0.05. And I don't have to worry about the issue of what do I do with several different p-values anymore, because I condensed all my information down to a single value, and then I built a reference distribution for that particular value. So to answer our research question here, no, we do not have enough evidence to support the research question. The p-value, which is 0.16, is not less than 0.05. And then you can write a conclusion from there. All right, I think I'm going to stop here now before going on to page 14. I'll just make that a separate video. That'll help keep the videos a little bit smaller in size. So let's go ahead and hit pause here, and then I'll make a second video on understanding variation when I have unequal proportions. All right, we'll see you in a minute.